So welcome back. In today's lecture, we will be discussing Raman spectroscopy. We have already discussed rotational and vibrational. So we'll be discussing Raman spectroscopy, and then we will also discuss what are atomic motions, what are different normal modes. So let us start today's lecture. Go to Raman spectroscopy. So this is highly useful spectroscopy, and it's discovered by C.V. Raman, for which he got a Nobel Prize in 1930, right? So let us see. So you have light, and light is falling onto a molecule. Let's say this is my molecule, right? So it can have different phenomena of absorption and all, but there is one phenomena which is called as scattering of light, right? So this is scattering. And most of the scattered radiation, so we'll write most of the scattered radiation is of unchanged wavelength. And is called as Rayleigh scattering. So this is also called as elastic scattering due to the fact that there is no exchange of energy between light and the molecule. So incident wavelength is equal to scattered wavelength. This was discovered, I think, in 1871 by Rayleigh. And the intensity of scattered light is actually proportional to 1 by lambda to the power 4. And this is the reason why sky appears blue. Sky is blue and sun appears red during the morning and evenings. So try to find out, try to read more about this Rayleigh scattering. So we are not going to go into more details why sky appears blue and all. So, or you must have seen this in some course, right? Okay. So now let us discuss what is Raman scattering. This was observed in 1928 by C.V. Raman, a name which does not need any introduction, right? And he got 1930 Nobel for this Nobel Prize. Right? Okay, so what does Raman scattering say? So if you have a molecule and you have a light which is incident, so lambda incident, so you have, let's say, a scattered light, lambda scattered, which is Rayleigh scattering, or elastic scattering. But in addition to this, there is also inelastic scattering. Okay, so lambda inelastic, lambda inelastic. That is also possible. Now, what happens basically here? If there is inelastic scattering, that means there is exchange of energy between the incident light and the molecule, right? And that exchange of energy can lead to increase or decrease in energy of the wavelength of this light, or increase and decrease in the energy of the light or the wavelength, vice versa, right? So I can say that if lambda of scattered light is equal to lambda of incident, then this phenomena is Rayleigh scattering, right? Now if lambda scattered is greater than lambda incident, so that means there is increase in the wavelength, then it is called as Stokes Raman scattering. And similarly, if lambda scattered is less than lambda incident, then it is called as anti-Stokes Raman scattering. Okay, now why does it happen? Why there is exchange of energy? Why there is inelastic scattering? So you can say vibrational or rotational transitions accompanying the scattering process cause or causes Raman scattering. So when you're shining light onto a molecule, there is a possibility of scattering, and along with scattering, there is also a possibility of vibrational or rotational transition. If all of it is happening simultaneously, then it causes Raman scattering. So then we can say that if we talk in terms of nu bar, so scattered light, the wave number of scattered light is equal to wave number of incident light plus delta E rotational or vibrational, whatever is happening, right? So then I can say that delta E rotational slash vibrational can be measured by this change in wave number, right? And this is called as Raman shift. Now it's a very small fraction, so only a small fraction, that is 1 part in 10 to the power 6 of the incident radiation is scattered inelastically. So why is that? That is because Raman effect depends on something called as polarizability tensor, which is denoted by the term alpha. So now what is polarizability tensor? It is basically ability to induce dipoles. So when you're shining light, it has some electric component which can induce the dipole moment in the molecule, and that ability is called as polarizability tensor or polarizability, which is measured by polarizability tensor. So just like scalar quantities, vector quantities, there are tensor quantities. So this is a tensor quantity, polarizability tensor. So now let's say if we have, considering induced polarization density which can be written as mu as a function of of the electric field. So I know there's a lot of writing here, but I think it is important to understand what is different, what are different type of spectroscopy, so that in the later part of this application there is no confusion. The polarizability tensor alpha ij is defined as the derivative of mu with respect to E. Because the change is happening, the polarizability is, or the polarization is being induced because of E. So that's how the polarization density divided by E will give you alpha, right? So we can say alpha is equal to mu by E, which is induced dipole moment, and this is the electric field that induces this dipole moment. Electric field that induces this dipole moment. So this is easy now, and this is the polarizability tensor. So this is polarizability tensor. Now we can say that the Raman effect is caused by the induced polarization of molecules that are scattering the light. If they are getting polarized, so they will cause Raman effect, and that is in turn caused by the electric vector of the electromagnetic radiation, right? So what we can do is, for an isotropic molecule, go back and read what are anisotropic molecules. We are not going to discuss what are anisotropic molecules, so go back and read a little if you do not know. So mu x, mu y, and mu z is equal to alpha xx, alpha xy, alpha xz, alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz. So same thing which you had written there, now we are writing in terms of matrix, right? So you have electric field vector Ex, Ey, Ez. Okay. Now the diagonal components are the values of alpha along x, y, and z axis of the molecule. Now, and you can see that the longer bond will be easier to polarize than a shorter bond. Like if a bond is stronger, then it will be difficult to polarize, and so on and so forth, right? So let us also discuss what is we have already seen what is transition dipole moment, right? When we were discussing selection rules. So transition dipole moment for vibrational spectroscopy is given by psi v mu and psi star, we can say v plus 1 d tau. Now if you remember that mu is here, mu is alpha e, but mu is nothing but ei xi plus ei yi plus ei zi, right? If you remember that discussion, and this will have x, y, and z components, and those components can then be treated as the basis for IR representations which transform as x, y, or z as the basis, right? So these will have their own IR representations, right? To which this will form basis. And IR representations for these wave functions can also be determined. So you can determine whether this integral will go to 0 or not, and accordingly define whether a particular transition will happen or not. Now similarly, we can put alpha e here. So e will come over here, and you have same states. Let's say, let's just call it as prime and double prime. So you have alpha d tau. Now alpha matrix, if you see, it has terms as xx, xy, xz, yx, right? So these are the binary products of unit vector transformations. So these will transform as so the components of alpha will be, so we will write down components of alpha. There will be 6 components because it's a symmetric matrix. Alpha xy is equal to alpha yx. So there will be alpha xx, alpha yy, alpha zz, alpha xy, alpha yz, and alpha zx. Okay, so 6 of these components will be there, and all of these will form basis for an IR representation, and corresponding IR representations for wave function are also known. So you can find out where the Raman effect will be seen and where it will not be, right? So all of this can be, group theory rules can be used to identify that. Okay, that should be easy to now see. Okay, so next topic that we are going to cover is atomic motions. So what are atomic motions? So let us consider a diatomic molecule AB. Now this particular atom A, it can move in any direction x, y, z, right? If this is x, y, z, it can move either in x direction, y direction, z direction. Similarly, this particular atom can also move in x, y, and z direction. Now what happens, or let's say if it moves in any arbitrary direction, then you can always think of those motions as, project those motions onto x, y, and z, and basically say that these motions are happening either in x, y, or z direction, right? So any motion can be projected to x, y, and z axis, right? So it will have some x, y, and z component even if it's an arbitrary motion. So this gives a possibility of 3 into n motions, which are called as degrees of freedom. So for example, a diatomic molecule will have 3 into 2. So n is the number of atoms. Number of atoms. So a diatomic molecule AB will have 6 degrees of freedom. Similarly, a triatomic molecule, let's say water, will have 3 into 3, 9 degrees of freedom, right? So you can easily calculate how many degrees of freedom or how many possible motions are possible, right? Different type of motions are possible. Now, these motions independently, these 3n motions, 3n degrees or motions give rise to 3 different type of motions, which are translation. A molecule can translate in any particular direction, right? That is one motion. A molecule can rotate, or a molecule can vibrate about its mean position, right? Now let us see how this can happen. So let us first see that what are the different. Okay, let's see how this can happen. Let's see if we have the molecule is like this in XYZ frame. So you have, let me draw the molecule with a different color. So I have A and B. This is my molecule. Now let's say if these two atoms, if both of them move in x-axis, along x-axis, right? That is possible. That is one way of moving. Out of 6, one way of moving is this. Second way of moving is this, along y-axis. Third way of moving is both the atoms will move simultaneously in one direction, which will give you 3 degrees of translational motion. Now, any given molecule, it is possible for any given molecule. I'm just taking example of a diatomic molecule, but any given molecule should be able to do this type of motion where all the atoms are either moving in x direction, y direction, or z direction, or if it is moving in any random direction, you can still get the projections onto x-axis, y-axis, and z-axis. So there must be, every molecule must possess 3 translational degrees of freedom, right? Or 3 degrees of translational motion. Either way you can explain. Now let us see what are the other possibilities. Okay, so let's draw this molecule again in the same frame. X, Y, Z. A and B. Now let's say if I say that A moves in this direction and B moves in this direction, right? Now they are not moving in same direction, which was causing the translation. If A moves in this direction and B moves in this direction, effectively they are rotating about x-axis, right? So this is one rotational degree of freedom, right? Similarly, if A moves in positive x-axis and B moves in negative x-axis, this will move in with respect to y-axis, right? So this is rotation about x-axis. This motion is rotation about y-axis. And third is like if they move about z-axis, how would you define? So there would be third motion, which can be defined by moving about z-axis, which will not happen in this case, or which will happen, but it will not cause any change in the molecule, right? For quantum molecules, you will not be able to, quantum objects, you will not be able to identify whether a change is happening or not if it is moving about its own axis. So there would be 2 degrees of rotational motion. Let us also take an example of a non-linear molecule, so that we know that for non-linear molecule there should be 3 such degrees. Let's try to see if we can, or let us take it as a home assignment rather, right? So home assignment, again it will depend upon how you can visualize. So show in a Cartesian coordinate system that a nonlinear molecule will have 3 degrees of rotation. Okay, so that you should be able to draw and sketch it out, right? So if there are 3 translational, 2 rotational, so what is left now? So out of 3n, we have translation possible. We have seen that 3 will be contributing to translation, plus rotation possible. So rotation, it will be either 2 or 3, depending on whether it's a linear or non-linear molecule, right? This is for linear and this is for non-linear, right? So the rest of the degrees will be vibrational degrees, right? So for example, if A moves here and B moves here, it will cause vibration of the bond. If A moves downwards, B moves upwards, then also it will cause vibration of the molecule. So rest of the degrees are vibrational degrees of freedom, right? So we can say here that vibrational modes is equal to 3n minus 5 or 3n minus 6. This is for linear molecules and this is for non-linear molecules, right? So this is easy to see. Now you can also appreciate the fact that each of the normal modes can be translational, rotational, or vibrational, or we can write down here translational, rotational, vibrational, forms a basis for IR representation of the point group. See, everything in this course, you go and then finally it will form a basis for IR representation of the point group, right? So that is how the beauty of this subject is, that you can actually correlate everything to the symmetry of that particular molecule and then talk about the physical properties, right? So here, each of the normal mode form a basis for IR representation of the point group of the molecule. We will see how to use this in next class by doing local coordinate analysis, and we'll see how to actually find out the different vibrations, how to visualize different vibrational modes. That is all for today.